Do 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 do. Welcome to AP Chem Video. How do you like that theme song, huh? Huh? It was Harry Potter. That's okay. Anyway, I hope you guys are well. Today we're going to talk about KSP. A lot of this stuff is going to be reviewed from that POGIL activity, but I think we'll clarify some things. So, let's get started. First of all, you know what? KSP is all about the solubility rules. So if I gave you this list here, which of these do you think would be insoluble in water? Okay, so if you look at the list, you're going back in your head, you're remembering stuff like PMS is insoluble and CBS, if barium, strontium, lithium, stuff like that. Okay, so what do you see here? So the ones that jump out to me, all alkali metal compounds are always soluble, so they would not be precipitates. They would be completely soluble. So we're not talking about those two. Ammonium compounds also, like the alkali metals, are always soluble. So basically, this whole chapter is about compounds like C. In earlier chapters, we would say they're insoluble, but now we're learning that, well, you know what, they do dissolve a little bit, and how much they dissolve is basically what KSP is all about. Okay, so moving on. Some really easy, well, first of all, writing K expressions. So this is how we write out the equilibrium expression for something dissolving. So barium sulfate breaks into the barium ion and the sulfate ion. And this would be our equilibrium arrow. So you guys can go ahead, and I want you to go ahead and write the KSP expression. Don't forget about the coefficients and about the stoichiometry. So go ahead and fill this in, and then you can actually go ahead and fill in number 3, and we'll see if you've learned anything from doing that POGIL activity. So pause, fill in, and then continue. All right, so hopefully these are the answers you got. So you just have to remember that if there's a 2 in front, that means that that quantity, that concentration of silver, for example, is squared. All right, and then aluminum hydroxide breaks into aluminum ions and 3 hydroxide ions. All right, that looks great. So now what is KSP? Well, KSP is called the solubility product constant because it's the product, meaning multiplied, of the ions. All right, and from there, what is it really a measure of? So it's a measure of how much a given compound or salt will dissolve in water. The higher the KSP, the more the reaction pushes in the forward direction. So therefore, the more ions, and therefore the more soluble. All right, so let's start doing some problems with this. First one, these are pretty easy ones. So we're talking about lead bromide, and it's formed by mixing solutions containing lead and bromine. So in this particular case, let's say the bromine ion concentration was 0.15. What would the lead ion concentration have to be to make a saturated solution, or in other words, to be at equilibrium? So go ahead and give that one a go. Okay, pause, give it a go, and then check your answers. So time has passed. Let's see how you guys did. So there's KSP. So we are looking for the lead ion concentration, and you popped in the bromine ion concentration as given. Don't forget to square that. Now, there is no reason to double that. I know some of you guys may have been tempted to double that. Don't do that. Why? Because the lead and the bromine, they came from different sources. They came from maybe like lead nitrate and sodium bromide. In other words, it was like a double replacement reaction. So since they came from different sources, there's no reason why the lead and the bromine have to be in a 1:2 ratio. So you do not have to double that. It just is what it is. So there's my 0.15, but you do have to square it because that's part of the whole equilibrium piece, not the stoichiometry piece, in other words. So that does get squared, and then you just solve. So the lead concentration would be 2.0 times 10 to the negative 4th. And that would be a saturated solution. Or in other words, the solution would be at equilibrium. All right, so the next example, very similar, except this time it gave me the lead concentration of 0.15, and you had to solve for the bromine. Okay, so bromine was X. All right, so a little bit of math, and it came out to 0.0055 molar. So that would be the concentration of the bromine. Okay, so you know what? Two related but totally different scenarios. Whatever's given, you can solve for the other one. So these would both be equilibrium solutions of lead, bromide, and water. Their lead and their bromine, again, are not in a 2:1 ratio. Why? Because the lead and the bromine, they came from different sources. So that's okay. All right, so that's probably the easiest type of problem you can do. Now let's move on and try a different one. So soon you're going to find out in the book work problems and all that, it's going to ask you to solve for molar solubility or solubility. So basically, how soluble is that compound? Okay, and you can go both ways. You can calculate the solubility from the KSP, or you can calculate the KSP from the solubility. So a little terminology: molar solubility is the moles of solute, or moles of stuff, that actually dissolve in a liter of saturated solution. Saturated is code for at equilibrium. So that would be moles per liter. Often if you just see the term solubility, that's actually grams of solute dissolved in 1 liter of saturated solution. That would be grams of stuff per liter. Hopefully, I'll be pretty clear about which one I want. Pretty easy to convert from one to the other. Okay, so we kind of have this general little concept map, if you will, or a little progression, that if you know the solubility, you can get the molar solubility. Okay, the way you would do that is by using the molar mass, of course, of the substance. Okay, and then if you want to go from molar solubility to KSP, well, somewhere in the middle, you have to sort of break the molar solubility into its actual moles of cations and moles of anions, so you can plug it into KSP. So to go from molar solubility of the entire substance to the concentration of ions, you're going to have to use the mole ratio from the compound. So if this was an ionic compound, you're looking at, the ratio of the cation, like the little subscripts here, X versus Y. So let's do an example. All right, so our problem is the solubility of this bismuth iodide is 1.32 times 10 to the negative fifth, and that's in units of grams per liter, and I would tell you that in advance. So calculate KSP for this compound. So looking at this sort of concept map, we are here, and we're trying to get here. Okay, so I would pause and go ahead and give this a go. This is definitely something that you did in the Pogo, and I think you guys can do. Okay, and then, but if you get stuck, then go ahead and play, and I'll sort of walk you through it. All right, so first step is, here's my gram solubility, so it's grams of bismuth iodide per liter. So I'm going to convert it to moles per liter. Now keep in mind, this is the molar mass of the entire compound. So now this is my molar solubility. Okay, so this is how much of the bismuth iodide in total would dissolve. So that's this step and this step. And now how do you get the ions? Well, if this is my bismuth iodide, there's 1 bismuth per every 1 bismuth iodide and 3 iodines for every bismuth iodide. So that's what we take into account next. So then your ion concentrations would look like this. So here's my bismuth, they're equal concentration. And then my iodide is 3 times that because of the 3-to-1 ratio. So those are my actual ion concentrations swimming around in the saturated solution. Well, now I can go ahead and plug that into KSP. So KSP is the bismuth ions times the iodide ions raised to the 3rd power. So we just plug those numbers in. And don't forget about that 3rd power. So in essence, you multiplied the number by 3 to deal with the stoichiometry, but then you cubed that concentration to deal with the equilibrium aspect. All right, there you go. So the KSP for this guy, 6.8 times 10 to the negative 30th. Not very soluble. All right, so what else can we do? We can go in the opposite direction. So we can go from KSP and then calculate the molar solubility or the gram solubility. All right, let's give it a go. Calculate the molar solubility of barium fluoride. The KSP is 2.4 times 10 to the negative fifth. So how much barium fluoride would actually dissolve in a liter of solution? By the way, we talked about this, I know, in one of my bells. Fluoride compounds, you might have thought they'd behave like chlorines and bromines and iodides. Those guys are pretty soluble, but fluoride compounds, surprisingly enough, are not very soluble. All right, so let's take a look. I think you definitely want to at least think about an ice table in your head for how to set these up. So barium fluoride is breaking into barium ions and 2 fluorine ions because of the stoichiometry. Now, I don't know how much barium fluoride I start with. Some amount does not really matter, but the key is whatever amount of barium fluoride I put in, some amount will dissolve. Okay? And then, so this will go down, and then my barium ions and my fluorine ions will go up. Okay? And they're in a 1-to-2 ratio on this side. So at the end of my ice table, the basic idea here is that the barium and the fluorine are in a 2-to-1 ratio. So now, when I plug that into the KSP expression, it looks something like this. So KSP equals the number given equals X for the barium and 2X for the fluorine raised to the 2nd power. Gotta be really careful with your math and make sure and simplify this properly. That 2x squared is actually 4x squared. Okay? Times another x is 4x cubed. All right, so you got to be really careful with that. All right, then you can go ahead and solve. So divide both sides by 4, and then take the 3rd root, okay? or basically whatever quantity you have raised to the 1/3 or raised to the 0.333, and you get a value of x equals 0.018. So x, what does x equal? X equals a couple different things. X equals the amount of barium fluoride that actually dissolved. So this really means that the 0.018 molar equals the concentration of barium fluoride that dissolved, which, if you needed this information, equals also the barium 2 plus ions that are in solution since they're in a 1-to-1. And if you wanted the fluoride ion concentrations, it would be this number times 2, right? So there you go. So that's how you can go from KSP to actually figure out how much of the substance is actually soluble. All right, and then could you easily take this to gram solubility if you needed to by using the molar mass of barium fluoride? I hope so. What else we got here? Well, here's a problem for you to do. So this is calcium phosphate, and I gave you the KSP. Pause here and please work through this one. Okay, and then when you're done, check your answer and see if you got it right. All right, so here's my equilibrium. Now this one, it's got a lot going on in this compound. So there's 3 calciums to every 2 phosphates. So the ice table looks a little something like this. This is what I was telling you about really keeping an eye on your math. So you get 3x cubed and then 2x squared. So if you simplify that all, now keep in mind, I know 3 times 3 is 9, but 3 cubed is 3 times 3 is 9 times 3 is 27. Okay, and then 2 squared is 4. Then if you multiply those, you get this magic number 108. That's actually going to come up a lot. You'll see that in a couple different instances. And then when you kind of simplify that part, the 3 and 2 are additive, so it ends up being 108x raised to the 5th. Okay, and then there's your KSP, and you can simplify, divide both sides by 108. Okay, and then raise that to the raise that to the 1/5, or I guess the 0.2. Okay, so whatever you do mathematically, and this is what you get. So the solubility of calcium phosphate means that this concentration of calcium phosphate will actually be dissolved in a 1-liter solution. And if you wanted to, you could calculate the calcium ions and the phosphate ions respectively. All right, so are we doing all right? What can we do with this information? Here's a last little scenario that you guys could look at. So what I gave you was a couple salts and their KSP values. And I want you to put them in order from most soluble to least soluble. Okay? Now, be careful. Sometimes, the solubility is directly related to KSP. No question about it. But sometimes that solubility, there's some things going on with the stoichiometry, and you can't just look at these numbers. So what I want you to do is go ahead and calculate these. Calculate the solubility, how much of that solid will dissolve in a liter of solution, and compare those numbers and see how they compare to the KSP. All right. Now we are going to do a second video, and this is where we're going to stop, but we're going to pick up with this question. So work it out, I should say. And when we start the next video, this is the first thing that we're going to go over. All right. I hope you guys are doing well. I'm going to sign out, and I will return sometime later. Have a good day. Okay, that's enough of that.